Alright, in this video here we're going to talk about how to prove trigonometric identities. So we have some guidelines that we can use to prove trig identities. First one, what a trig identity is like an equation where we have like two complex or one or two complex trigonometric expressions that are equal to each other. So the first thing we want to do is start with the more complicated side of the equation. It's usually easier to go from the more complicated side and simplify it and turn it into the less complicated side than it is to start with the less complicated and change it into something that's more complicated. All right, so we start with the side that seems more complicated to us. We convert things to sines and cosines. So if we have tangents, cotangents, secants, and cosecants, it's a good idea to convert those into sines and cosines so that everything's in terms of those same two functions and we can work with those. And then we use known identities and algebraic techniques. Right, so we know some trig identities, the reciprocal identities, the Pythagorean identities. So any one of those ones we know we might have to use algebraic techniques like factoring, finding common denominators for fractions so we can add and subtract them. So all that kind of stuff we do. And if you watch the other video that I just did on simplifying trig expressions, basically we're doing here just like what we did in that video in those examples. We're just working on the expression we have, trying to combine things together, trying to simplify things, and trying to, step 4, change it to the other side of the equation. Right? So again, if you watch the video that I did on simplifying trig expressions, we had something complicated and we had to work on it and make it something simpler. Right? The problem with those types of problems is sometimes it's hard to know where to stop. Well, when we're dealing with trig identities, they're giving us both sides of the equation. So we know what the goal is. We know what we want to make it equal to. So we just have to keep on working on it until we make it equal to whatever's on the other side of the equation. Right? So these problems, if you watch that one that I did on just simplifying trig expressions, these types are a little bit easier because we know what the goal is. We know what it's supposed to equal at the end. So we kind of can use that to decide how to proceed through the problem. All right, so those are our basic guidelines for proving trig identities. I am going to pause the recording, erase those steps, and then put up the first example that we'll do where we kind of walk through how to do this. All right, so for this first example we're going to do, we have cosine theta times the quantity of secant theta minus cosine theta equals sine squared of theta. And we want to prove that these two things are equal to each other. Right, so what we do is we start with one side of the equation and we pick the more complicated side. And sometimes that's a judgment call on your part, which side seems more complicated to you. To me, the left side definitely seems more complicated. It has this multiplied by this. There's a couple of different trig functions in here, whereas the right side is just a sine squared theta. Right, so to me the left side definitely seems more complicated. So I'm going to start with that more complicated left side. So the way we write this usually is LHS. Right, that stands for left-hand side. Right, so I'm starting with the left-hand side of the equation equals, right, cosine theta times secant theta minus cosine theta, and then I'm going to do work with this and simplify it and combine things together and all that stuff, and at the end show that it equals sine squared theta, which then equals RHS, the right-hand side, and then I prove that the left-hand side equals the right-hand side, so I prove that this identity is true. Right, so that's how these problems work. You start with one side, you do work on it, you use your factoring, your algebraic expressions, you combine fractions, you use your trig identities, you turn it into the other side, and then you're done. Right, so again, the advantage of this type of problem as opposed to just simplifying trig expressions is we know exactly what our goal is, exactly what we're aiming for. We need to turn this into sine squared of theta. All right, so we just got to make it happen. All right, so first thing, if I'm following those guidelines, right, I started with the more complicated side. Now I'm going to turn everything into sines and cosines. Right, so most of what I have here is already cosines, right? So cosine theta times, and now secant theta, remember secant is the reciprocal of cosine. So let me write that as 1 over cosine of theta. Right, so changing everything into sines and cosines. In this case, everything is in terms of cosine, which seems weird because in the end it has to equal sine squared, but we're being told that these two things are equal. When you're asked to prove a trig identity, you're not going to be given one where they're actually not equal, and it's like a trick question. It's like you spend 7 hours working on it, and like I can't get this to equal the other side, and then the person who wrote the problem is like, ha, they don't actually equal, you just wasted all your time. It's not like that. This does equal that. We know that that's equal, we just have to show that it's true. Right? So we know that somehow when we work on this, it's going to equal sine squared theta. All right, so next thing I'm going to do, since I have something outside of a parentheses that involves subtraction, well, I can do that algebraic thing when I have something like that, and distribute that into the parentheses. Right, remember, the rules of algebra, even though we're doing trigonometry now, all the rules of algebra still apply. Right, so I can still use the distributive property to multiply something into a parentheses, which is what I'm doing. Right, so when I do cosine theta times 1 over cosine theta, that's going to equal cosine theta over cosine theta, which just equals 1. Right, so it's going to be, that's a weird looking 1 there. So that's going to be a 1 minus, and then cosine theta times cosine theta is going to be cosine squared of theta. All right, so I get 1 minus cosine squared of theta. Right, so when you multiply something times its reciprocal, that's going to equal 1 every time. Like if I multiply 5 times 1/5, that's 1. Right, if I multiply 2 times 1/2, that's 1. Right, something times its reciprocal. Cosine theta times 1 over cosine theta equals 1. Right, it's no different from any other pair of reciprocals that you multiply together. And now we get 1 minus cosine squared of theta, and we're being told that we need to somehow make that equal sine squared of theta. Well, once again, right, if you watched the video that I did on the simplifying trig expressions, this property or this identity that I'm about to put up here came up in both of the problems there, and it comes up all the time, right? The identity that says sine squared x plus cosine squared x equals 1, right? Anytime you're doing one of these problems and your equation somehow involves a cosine squared or a sine squared, you should be thinking about this property here, or this identity here. Right, sine squared x plus cosine squared x equals 1. All right, so, well, what I have here is 1 minus cosine squared of theta. So can I turn this into a 1 minus cosine squared? I can, right? If I subtract cosine squared of x from both sides of the equation, I get on the left side just the sine squared x by itself equals 1 minus cosine squared of x. And so this expression here, 1 minus cosine squared of x, equals sine squared of x. All right, so 1 minus cosine squared, that's equal to sine squared theta, which is the right-hand side of my equation. And so I've just proved that the left-hand side equals the right-hand side, and so I've proven that this identity is absolutely true. Right? So just this little part here is something new that you might not have seen before. But again, anytime you're doing one of these problems, whether it's simplifying the trig expressions or proving the identities, anytime you see a cosine squared or a sine squared, you always have the option of going to this identity, sine squared plus cosine squared equals 1, and you can rearrange it if you want to. Right? It doesn't always have to be my equation says sine squared plus cosine squared, and I replace that with a 1. In this case, my equation says 1 minus cosine squared. Well, okay, let me subtract the cosine squared to the other side. So I have 1 minus cosine squared, and then show that that equals sine squared of x. And so I can replace 1 minus cosine squared theta with just the sine squared of theta, which is the right-hand side of the equation, and we're done. All right, so again, this identity here, sine squared plus cosine squared equals 1, it comes up all the time. It's a really important one to know, and also to be able to manipulate, to move stuff around. If it doesn't show up in exactly this form, it's still useful. All right, so that's our first example of proving the trig identity. I'm going to pause the recording here and put up another one and go through one more example on this video. Next example, we got 2 tangent of x times secant of x is equal to 1 over 1 minus sine of x minus 1 over 1 plus sine of x. All right, so again, this is an identity. This is true. These two things are equal to each other. We just have to show and prove that they are equal. All right, so first thing, start with the more complicated side of the equation. Now in this case, both sides seem pretty complicated, but the one that has the two fractions being subtracted is going to be the side that I want to start on, because it's going to be real hard to take this and somehow separate that into two fractions being subtracted. Whereas if I start with two fractions, I can find common denominators and combine them together into a single fraction, which hopefully will lead me to this thing over here. All right, so in this case, I'm going to start with the right-hand side of my identity. Right, the last example we started with the left-hand side. This time we start with the right-hand side. You can start with either side. It's up to you. So don't feel like you always have to start with the left side just because it's on the left. You know, if the right side seems more complicated, or it seems like it's going to be more advantageous to start there and work with that, then start with that side, right? Which is what we're doing here. Right, so 1 over 1 minus sine of x minus 1 over 1 plus sine of x. All right, I have two fractions being subtracted. I need to find a common denominator and multiply things to get the common denominators and then actually combine the fractions together. So my two denominators, 1 minus sine of x and 1 plus sine of x, the common denominator is going to be those two things multiplied together. All right, so for the first fraction here, I'm going to multiply the numerator and denominator times the denominator of the other fraction. All right, so I'm basically taking this first fraction and multiplying the top and bottom by 1 plus sine of x. Right, and that's going to create that common denominator so that it has both of these factors. And for my my second fraction, I'm going to multiply the numerator and denominator by the denominator of the other fraction here, 1 minus sine of x. All right, so I multiply that on the top and bottom. And remember, I'm allowed to do that because when I multiply by 1 over minus sine x over 1 minus sine x, I'm really just multiplying by 1, right? Multiplying by the same thing over itself doesn't change the value of what you've got. All right, so I do that, and now I can go ahead and actually combine my numerators together because now my two fractions have a common denominator. All right, and this is just like what we did when we're dealing with rational functions and rational expressions to find common denominators. Right, just because there's trigonometry here doesn't change how we approach dealing with fractions. All right, so 1 times 1 plus sine x, that's just going to be 1 plus sine of x. Now, careful here. This is a negative 1 that I'm distributing here. So that's going to be a minus 1 and then a plus sine of x. Over, and then in my denominator, I think I'm going to actually have to multiply that denominator together. So if I FOIL my denominators here, 1 times 1 is 1. 1 times plus sine x is going to be plus sine x. 1 times minus sine x is going to be minus sine x. And then negative sine x times positive sine x is going to be minus sine squared of x. And those sine x's in the denominator are going to cancel out, and the positive 1 and the negative 1 in the numerator are going to cancel out. So I'm going to end up with, in the numerator, 2 sine of x, right? Sine x plus sine x is 2 sine x, which is a good sign because I do have a 2 up here, and now my 2 finally showed up, so I'm pretty sure I'm on the right track. And then in the denominator, I have 1 minus sine squared of x. All right, so I get 2 sine x over 1 minus sine squared of x. So I'm not quite here yet, but I am getting closer. And once again, I see this 1 minus sine squared x. Just like in that last problem, that makes me think of sine squared x plus cosine squared x equals 1. If I subtract that sine squared x to the other side, I get cosine squared of x equals 1 minus sine squared of x. So I can take the 1 minus sine squared of x and replace it with cosine squared of x. Right, just like in the last problem, it was the other way. In the last problem, we had 1 minus cosine squared, and we replaced it with sine squared. Here we have 1 minus sine squared, but we can do the same thing, subtract the sine squared to the other side of our identity, and replace 1 minus sine squared with the cosine squared. All right, so again, anytime you're doing a problem and you end up with a sine squared or a cosine squared, you should be thinking of this identity here, and how can I use that to kind of rearrange things and make this work. All right, so this is going to now equal, and I had to erase what's up there so that we had enough room to finish this one off. So I'm going to have 2 sine of x over cosine squared of x. All right, the 1 minus sine squared, like we saw here, using that Pythagorean identity, I can replace with a cosine squared. Now here's the trickiest part of this problem. Right, it's been a little tricky so far. But to get a tangent x and a secant x, remember tangent is sine over cosine, secant is 1 over cosine. Well, I have a sine here, and I have 2 cosines in my denominator, so I need to break apart those cosines. All right, so I'm going to do 2 times, and then I'm going to do sine x over cosine x, and then I'm going to do 1 over cosine x. All right, so if I multiply this together, 2 times sine x times 1, that gives me a 2 sine x in the numerator. Cosine x times cosine x gives me a cosine squared x in the denominator. Now I have to do that so that I can get my final result over here, right? Because sine x over cosine x is tangent of x, and 1 over cosine x is secant of x, and then that's the left-hand side of my equation, and I've just shown that the two sides are equal to each other. All right, so that's another trick that we haven't seen in any of the examples I've done so far. But sometimes if you have something like this, a cosine squared, and you need to change it into 2 separate functions, you need to kind of like split it apart into 2 different fractions like I did here, sine over cosine and 1 over cosine, in order to get the tangent and the secant. Right? So it's another little trick that sometimes you have to pull out. And doing these problems is all about collecting all the little techniques, all the little tricks that you use, all the skills you need, and then it's like having a toolbox of things that you can use to solve the problems, and then just pulling out the proper tool at the proper time to do it. Right? So Check out the next video I do. I'm going to do some more.